I will go ahead and give the intro now. So we're very pleased today to introduce Matthew Walter, who is an assistant professor at the Toyota Technological Institute at Chicago. His interests revolve around the realization of intelligent, perceptually aware robots that are able to act robustly and efficiently in unstructured environments, particularly with and alongside people. His research focuses on machine learning-based solutions that allow robots to learn to understand and interact with the people, places, and objects in their surroundings. Matthew has investigated these areas in the context of various robotic platforms, including autonomous underwater vehicles, self-driving cars, voice-commandable wheelchairs, mobile manipulators, and even autonomous cars for rubber ducks. Matthew obtained his PhD from MIT and the Woods Hole Oceanographic Institution, where his thesis focused on improving the efficiency of inference for simultaneous localization and mapping. With that, I'm going to turn it over to you, Matt. All the best.
Thanks, Andrea, and thanks for the intro. And thanks for allowing me to visit, albeit again virtually. So my name is Matt Walter. I am at TTI Chicago, and for those of you who aren't familiar with TTI Chicago, we're sort of a strange entity. I guess I liken ourselves to Institute for Advanced Study at Princeton. So we're a philanthropically endowed graduate level CS institute. So we're sort of like a computer science department and university in one. We were endowed by TTI in Chicago, TTI in Nagoya, hence our name, Toyota. We're not affiliated with Toyota. We don't get discounts on cars or anything, but our endowment comes from Toyota. And we're small by many standards. So we have 11 tenure track and currently 10 research assistant professors. These are 3-year endowed positions, and that may fluctuate anywhere from 8 to 15. And even within computer science, we're focused on machine learning theory and what we call machine learning applications. So that's computer vision, robotics, speech, NLP, comp bio, as well as computer science theory. We have 42 PhD students, and we advise around 10 UChicago students. So we're very closely affiliated with UChicago, though we are technically independent. For those of you who are familiar with Kitty, we are the TTI in Kitty, and there's our website for more info. And we're located on UChicago's campus here, so on the south side of Chicago. And one of 2 shameless plugs. So TTIC is hiring, and that's for both tenure track faculty and research faculty. So tenure track faculty, it's a great position in my view. So it's very research focused. So we teach 1 quarter a year. That's 10 weeks. 10 weeks, but 20 lectures a year. But we get paid for the 9 months. Research assistant faculty, it's a hard money position, so paid by our endowment. It's a fixed 3-year position with no teaching obligations, though many do choose to teach. We've had many, about 65 plus research assistant professors or RAP alumni at leading institutions, with many coming from or going to Berkeley. So just a list of a few of the people. Bradley Stady was a student of Peter Abeels, he's here now, and Madhur Tulsiani is one of the faculty here. So if you're looking for a job in machine learning or computer science theory, please visit that link and consider applying. So I run the Robot Intelligence through Perception Lab. So we're focused on, as the name suggests, robot intelligence. I'm going to talk about a subset of the work that we do here, mainly involving some of the work by Andrea Daniele in the upper left and a couple of the other students here. But our work more broadly includes work on neural memory architecture. So this is work with co-advised by Michael Mayer, again, who was at Berkeley. He's now at University of Chicago. I have some students who are interested more in theoretical aspects of RL. That's Kazaya and Falcon. Some of my work relates to self-supervised vision or 3D vision in particular, so Jiading and Shengji. Some work on transfer learnings, particularly learning in the presence of visual distractors. That's Takuma. And then this idea of doing joint design and control. So jointly optimizing a robot's design as well as the control policy that allows it to locomote. So that's Chip Schaff. So we've done some work with rigid body robots, so learning the design of legged robots and then the control policy. And now working on that in the context of soft body robots. So that's our lab as it stands now. So again, it's not news to anyone here, but for the longest time, robots have largely been seen as machines that are used to do repetitive or dull tasks. So factory automation is the classic application, and still there are many uses of this. So this is a Tesla Model S factory, and here really the focus is on accuracy and repeatability. So doing the same task and doing it over and over and over again, these things that are dull, and in this case, may be difficult for people to do with the loads that they're lifting. And with advances in mitigating uncertainty, with planning and control and perception, we've been able to take robots off the factory floor into unstructured environments. So what I'm showing in this video here is arguably dated by today's standards. This is our team at MIT, Talos, our Frankenstein of a robot in the DARPA Urban Challenge in 2008, doing street level navigation with minimal dependence upon GPS, relying on multiple modalities of perception. In the bottom, I'm showing a 3D rendering of the RMS Titanic that was built with this ROV Hercules here, using images collected by the vehicle. So again, you're doing dangerous and difficult tasks in unstructured environments or semi-structured environments. And really, the capability that allowed this was being able to mitigate uncertainty. And what I'm interested in doing, as Andrea mentioned, is taking robots, not using them in unstructured environments distant from people where they're operating as their surrogates, but rather robots that are coming into our unstructured or semi-structured environments where they're able to work as our partners. So there are many applications in the upper left, in manufacturing, in logistics. So in the lower left is a robotic forklift that developed, way back 10 years ago or so, to do materials handling in semi-structured environments with and alongside people. I'm particularly interested in assistive technology settings, so allowing people with mobility or physical impairments to maintain their independence, whether it's manipulating things or a voice command of a wheelchair that allows people who cannot move on their own to navigate independently, as well as healthcare settings more generally. So that's where we want to be, robots as our partners. But if you look at where we're at now, it's largely interactions much like this. So this is a user of a Canovo Jayco arm, controlling this arm to retrieve juice from a refrigerator. And if you notice in the beginning of the video, and it should loop, he's controlling the arm using his foot, but controlling a joystick, basically using switch mode control of the individual joints on the arm. It's a very, very involved, slow process. So this is sped up several factors. I mean, it's great. He's able to do something that he would not be able to do on his own, but still it's a very involved process and requires significant training. On the bottom, I'm showing a video from the DARPA Robotics Challenge. This is MIT's team. So this is a rendering of Atlas manipulating a valve. And this team the robot was controlled by 3 or 4 operators, many with PhDs in robotics, interpreting the sensor streams from the robot, so the LiDAR point clouds and the various image streams, and deciding on foot level control, foot level positioning, and then end effector positioning for the arm. So again, very involved. This is not the type of interaction that I imagine, at least, if my grandmother is going to be controlling a robot. So arguably, a more natural way for people to command and control robots is using natural language. And that's what I'm going to talk about today, is how we can use natural language as a way of controlling robots and conveying information to robots, whether it's a robotic forklift where you'd like to be able to talk to it much as if there was a person in the seat. And that's really how I viewed it. I want someone to be able to talk to a robot as if there was a person there, either driving the forklift or controlling their wheelchair. And so that's where I would like to, I think we need to be really more natural and efficient means of command and control. And there's been a great deal of work in language understanding for robotics. So dating back to the work of Terry Winograd in the early 70s, much of the early work in this area would use language, albeit in a limited sense, to map fixed language structure to a formal logic specification of the robot's actions. And the early 2000s, with the advent of statistical methods, there were statistical approaches to what's referred to as symbol groundings, where you want to parse language either into formal action specifications or into symbols that model physical reference in the environment. So these are objects, places, paths, etc. And the key to these methods is they're not hard-coded, but they're learned from data. And so their expressiveness is limited largely by the richness of the symbol space and the richness of the data. So in the upper right, I'm showing a factor graph for a command where in this case, it's for our forklift. So the command is put the tire pallet on the truck. Those are the observed random variables. And the latent random variables are the symbols in the robot in a symbolic representation of the robot's state and action space. And more recently, we've seen an explosion of neural sequence-to-sequence models that in some sense, you can think of them as viewing this problem of mapping from human language, let's say English, to robot actions as a form of machine translation. So going from English to a robot language, if you will, typically with additional input modalities like language and vision. So these models are far more expressive, but they require, as you can expect, a larger and richer amounts of training data. And I should say, as I go along, if you have any questions, please feel free to interrupt me if anything's not clear. Just feel free to stop me. So the standard approach that I've taken with this and other people take is to view natural language understanding as probabilistic inference. So we have some probability model that we want to maximize, where we have as input the command. So that's the potentially multi-sentence free-form instruction. Put the tire pallet on the truck. And then we want to map this to the corresponding symbols in the robot's model of its state and action space. So that are objects that includes objects that the robot's aware of, actions and some behavior repertoire that the robot is able to execute, spatial relations, locations in the environment. And typically the way this is done, by far the most common, is to do this with a known world model. So the robot has full knowledge of the environment and the set of actions that that environment allows. And that is known a priori. And so we now search that world model for the set of objects, relations, actions, and locations that maximize this likelihood. And that's really the standard. And so typically, where does this world model come from? What we do is we take a robot and we drive it around, we collect LiDAR data, and we run, let's say, ISAM or some, whatever off the shelf, whatever your favorite SLAM algorithm is. And that gives us a floor plan. And then we'll go through that floor plan and we'll annotate areas. We'll label a room by hand and say, this is Matt's office, this is the lounge, this is the cafeteria, et cetera. And so some of my work that's related to what I'll talk about later is this idea of instead, rather than having to hand write this down by hand, learn this from language. So really allow a robot to follow you on a tour, much like you would with a new colleague. You'd walk them around the building and you describe where you are now. That's fairly easy to ground, but also take advantage of the fact that language has essentially an unlimited field of view, and it's able to convey information that's difficult to infer from LiDAR data and image data. So I can describe things that are outside the field of view to the robot and that convey semantic, topologic, and metric, albeit uncertain, metric information. And so we're able to take this with sensor observations from the robot to build up a map. And that was that pie chart that I showed earlier from just natural language descriptions of the environment. Okay. But now what happens if a robot is entering an environment that it's never been in before? What do? We don't have a map that we can ground things to. And so we formulate this again as an inference procedure. Forgive the change in notation now. Our goal is to maximize this distribution over the robot trajectory for some horizon, so capital T time steps into the future. But again, this could be symbols as well, using, again, of course, language. And this might be language that's accrued over time, hence the superscript T. The sensor data, so whether that's LiDAR streams or images acquired by the robot, and of course, odometry as the robot drives around. And this is what we would like to do. And typically, again, on the right-hand side, you'd have the world model, which again is this some known representation of the environment and then the actions made available to the robot by that environment. So what you can effectively do, and what we do, is introduce this world model as a latent random variable. So this is what we refer to as a semantic map, and I'll go into more detail of what that map looks like. And so that this equation, I don't have my pointer here, but that the probability of X given S, lambda, and Z, we know how to do that. We have various algorithms that allow us to do that inference. But of course, we don't know S. S is instead a latent random variable. So on the right, we have a distribution over S, and that's what we're going to do. And again, we introduce this behavior, and I won't go into too much detail on the behavior, but basically it's essentially capturing how a robot might, or an agent might explore an environment that doesn't know a priori, given a natural language instruction, as well as observations of what it's seen thus far in the environment. So I'll go through this. And we formulate this as one is a problem of map learning. So learning a representation of the environment or distribution over the environment from language, basically hypothesizing the structure of the environment. Learning a set of behaviors that are executable in that environment, given the command, and then policy learning. So actually executing these in the environment. I'll go through these in turn. And so why is this hard? Well, what we're trying to do is we're trying to fuse language with, sensor modalities that we're traditionally used to using, like LiDAR scans and camera images and odometry. And language provides very disparate information, and that's good in some sense, right? Really. So what's allowed us to make progress in estimation and robotics is exploiting the complementary nature of different sensing modalities, right? We have no one perfect sensor, or at least we're not able to, use what we think could be a perfect sensor. So we take all the different sensors that we can get and exploit their different benefits. And so that's another use for language. It provides advantages over other sensing modalities. The policy that's actually deciding on how to act is not acting based upon language and a known map, but rather language and a distribution over worlds. So it has to figure out how to behave given an uncertain environment. And the space of observations behaviors is large, and that makes this inference problem challenging. Okay, so I'll just go through how we do this, again, focusing on the mapping first. And so what we do, the basic idea here is, and with this line of work more generally, is to treat language as another sensing modality, like images or like LiDAR. Again, exploit as providing complementary observations of the environment. So the way that we do this in this case is this idea that as part of the instruction are these either implicit or explicit descriptions of the environment. And we refer to these as annotations. And so the annotations, say, for example, the command is go to the kitchen down the hallway. It's a toy example, but what we can extract from this is that the user is telling the robot that you're in an environment where there's at least one hallway and at least one kitchen. And then one of those hallway kitchen pairs is consistent with the kitchen being down the hallway. So that gives a set of spatial relations and a set of regions that exist in the environment. And so we can use that to hypothesize a model of the environment. And so the way that we do this, and again, I'll go through this relatively quickly, is using a conditional random field model we refer to as the hierarchical distributed correspondence graph. It's a bit of a mouthful, but it really is a conditional random field where the the observed random variables are language, so parsed parsed language, and the latent random variables are the set of grounding. So in this case, it's the set of regions that may exist in the environment, the objects, and the spatial relations between region and object pairs. And again, we formulate this as an inference problem where we're doing inference over binary correspondence. Again, I won't go into too much detail. It's a bit, admittedly, it's a bit ugly of a factor graph, but what we're seeing on the bottom are the observed random variables. So go to the kitchen down the hallway, and these actually should be shaded. And the gammas are different symbols that these could correspond to. So that could be objects, that could be regions, that could be spatial relations. And this phi is a binary correspondence variable. So when phi is true, that means a particular word or phrase corresponds to that particular symbol. And so there are advantages that I'm happy to talk about later to formulating it in this way in terms of making inference more tractable. And that's the way that we formulate this. So we enumerate all possible symbols that each one of these phrases could correspond to, and we search over these binary correspondence variables to see, again, which ones are true, those are the ones that the words correspond to. And again, we have a hierarchy, so it's sort of a course-defined way of doing this to improve inference. And I should say all the code that implements this and variations of this model is all available on GitHub with a new version, I think, coming out soon, if it's not out already. So we get out of this, again, this may seem trivial in some sense because what we're, as I'm visualizing it, but we learn that, again, go to the kitchen down the hallway is conveying this knowledge that you're in an environment that contains one region that's a hallway, another region that's a kitchen, and that they're consistent, at least one pair of those is consistent with the spatial relation whereby the kitchen is down the hallway. And so we take that and we use that to build a semantic model of the environment. And we refer to this as a semantic graph. So we have this S as a semantic graph, and it includes this topology G, some metric embedding, so the pose of each one of these nodes in the graph, and a set of semantic labels for each one of these locations. You can think of, loosely, you can think of each one of these nodes as being a region or an object in the environment. An edge here as encoding some relationship between these, so some spatial relationship between the regions. And then these bar graphs as being a distribution over the label for each one of these regions. And we want to maintain this distribution given the stream of sensor data, so LiDAR and images, for example, odometry, and most interestingly, language. Okay, so we formulate this, we factor this. This is no assumptions made. So I'm just applying chain rule here to break this down into different distributions. And on the right-hand side, what we have is a distribution over topologies or graphs given language. And so getting back to the earlier example, there's a kitchen, or go to the kitchen down the hallway, we infer that, again, there is at least one region there's a kitchen, another region that's a hallway, and then at least one pair has this relation where the kitchen is down the hallway. So with this, what we do with that is we take that and we employ a set of hypotheses over the topology of the environment. So we hypothesize essentially different worlds. And while that is in theory combinatorially large, in practice, most man-made environments have walls, and so that limits the connectivity of the environment. So really, there's a small subset of the potential topologies that are actually have non-zero likelihood or non-negligible likelihood. So we modeled the space of hypotheses, again, using a sample-based representation. So that's what I'm visualizing here, a set of n different samples or particles, each with their respective weight or likelihood. And then for each one of these topologies, this introduces what we refer to as a Gaussian Markov random field. So this actually gets back to some of my thesis work that Andrea was talking about, where if you imagine each one of these graphs, again, nodes have some metric embedding, their location. Edges model some spatial constraint. And if you model that likelihood as being Gaussian, you get a Markov random field, as I'm visualizing here, and particularly a Gaussian Markov random field. And so if you parameterize this in the Gaussian form, or represent this as a Gaussian rather, and you parameterize it in what's referred to as the information form. So we're most typically used to dealing with representing a Gaussian in terms of a mean vector and a covariance matrix. But alternatively, you can represent it as a information matrix, which is the inverse of the covariance matrix, and that's sigma inverse or often lambda. And then eta, which is referred to as the information vector. And that is the nice property that the structure of the information matrix encodes the structure of the graphical model or the factor graph. So where we have a non-zero entry in this information matrix, that means there's an edge in the graphical model. And similarly, no entry in the information matrix or a zero entry implies no edge. And so what you can do is, again, because the environment is probably not going to be fully connected because these are man-made environments, you can exploit this sparsity to do inference in linear time. So if you're familiar with a Kalman filter, that inference is quadratic. And nominally with the information filter, it's potentially cubic, but you can exploit the sparsity to do this in constant time. And so that's what we do to essentially relax this sample-based representation, which effectively gives us a pose graph. And then we relax it to get the actual metric embeddings. That's what I'm visualizing there. Let's see. And then we have the semantic distribution we model using a Dirichlet distribution. So just a toy example again with this. So go to the kitchen down the hallway. The robot started navigating. So these colors indicate the semantic nature of the region. So as the robot's driving, it was in a lab. So that's that chartreuse puke-like color. And then it hypothesized, again, a set of particles hypothesizing different models of the environment. And so these are different locations of hallways as these orange circles. And this is a small subset of the particles. I think we typically operate with maybe with 100 particles. And so each orange location is a hallway. Each blue is a kitchen. And I'm not visualizing the edges, but there are edges that connect various hallways to kitchens. And some particles might hypothesize that there are several kitchens, maybe one kitchen having several hallways, maybe one hallway having a kitchen that's quote unquote consistent with being down from the hallway. This is its visualization of its hypothesis of the world. And using what I'll get to in a bit, we use this to infer what is the right set of behaviors and what's the best action to execute to navigate. And as the robot navigates, it observes, say, in the context of a LiDAR scan, a narrow section that it's learned, and it's learned represents a hallway. So we have a trained classifier that takes in LiDAR data and learns how to assign a semantic label to areas. And then it might see a microwave or a refrigerator, and it's able to recognize that area has a high likelihood of being a kitchen. So as it navigates and its observations are inconsistent with various hypotheses, their likelihood goes down. As other hypotheses are strengthened by observations, their likelihood goes up, and then it ends up being peaked. And again, in this case, again, I don't know if I you can see my pointer here, but there is one location of a hallway that it didn't navigate down. That actually is a valid hallway. So it is still hypothesized that there might be another kitchen down that hallway as well. But it's navigated to one and found it, deemed that the command was satisfied. So we have this distribution. And now what we want to do is we want to infer what is the right policy to execute. Again, we want to do this over the space of distributions, not a single map. Doing this within the context of a single map would be trivial. So we formulate this as a planning under uncertainty problem whereby we solve our one-step policy, where we take as input our distribution over worlds and we output the next action. And this is a path to a particular location in the environment or a stop. So when it outputs stop, it's deemed that it satisfies the command. And this is fairly, obviously a fairly traditional way of dealing with this. And then the way we approach this is we minimize some cost function. And I'll talk about what that cost function looks like. So we take our distribution and we model it using a set of features. Again, these are hand designed features at the moment, based on earlier work. So we have path geometry, landmark geometry, and relative path landmark geometry. Of course, again, we have a distribution over worlds. So the way that we represent these features is using a RKHS, a reproducing kernel Hilbert space embedding using the first K moments. I believe we look at the first 2 or 3 moments. And then we use those to define our features. And then what we do is we express our cost as just a linear combination of these features. And so what we want to do is we want to learn these weights. And so we collected a bunch of demonstrations where we gave people instructions and asking them to navigate in an environment they've never been in before. And we followed them. And then we use that, and again, assuming that they're acting optimally, we minimize this multi-class hinge loss. We learn the set of weights such that the behavior of these humans is optimal under that cost function. Again, a fairly standard approach to inverse optimal control or inverse RL. Again, with some regularization penalty. And of course, as we're training the policy, the robot's going to be taking actions that were not seen during training, and so we employ a fairly standard method, Dagger, whereby we alternate between collecting data and then refining the current policy based on states that were visited. So we tested this out on a number of different platforms. Some of this work was developed under the robotics CTA. And so that uses this Husky platform. So we have a couple of these Huskies that we were testing on, as well as our voice commandable wheelchair. And we consider a couple variants. So one is doing this with a known map. So sort of the gold standard. We have a fully annotated map of the environment. It's really just but it's a language grounding problem. Language grounding tells us where the goal is, really a distribution over the goal. And then we employ some standard, RRT star like planner to get there. The next baseline that we consider is an unknown map where we infer the commands, but we don't use language to infer anything about the environment. We just rely on the environment being updated as the robot navigates the environment. So essentially, it's not using language as a sensor. The robot will effectively opportunistically use the model of its environment that it's built, and then as it navigates, grow that environment and hope that it essentially stumbles on the destination. And then the third, of course, is our method, where we infer commands and annotations from language. And we do this in simulated and real world settings. And so on the left, I'm showing the results of a simulation. And so what I'm showing is a plot of distance. And so not surprisingly, the distance traveled by the robot before it got to the goal is lowest with the known map. So essentially just infers where the goal is, and it takes what it believes is the shortest path to get there. On the other extreme is not using language as a sensor. So doing this where you just opportunistically hopefully stumble on the goal destination. And that results in paths that on average are about twice as far with the known map. With our method, we find that the robot takes paths that are longer than with the known map, but not by much. So roughly, under 4 meters longer travel with our method by exploiting language as a sensor, hypothesizing the structure of the environment, and then using that hypothesis to guide its motion. When we do this with the physical robot, we actually find that our method is comparable using our method is comparable to having a known map. The mean is actually lower, but that's not statistically significant. and roughly half the distance traveled when not using language. And we've done this for other domains like mold manipulation. So this is a rendering of a husky. So it was given the command, retrieve the ball from the box. So it's a husky with the UR5 arm on it. It's in an environment with a bunch of boxes, chairs, suitcases, etc. And one of these boxes has a ball in it. And this is 22 seconds in, so it started navigating. What these cubes indicate are locations of a box, either observed or inferred. The one that's solid green is the one that it's navigating to currently. So it has observed actually a box at this point in time, and it's hypothesizing that there's a ball inside the box. Again, using that as inferring that annotation, and it navigates there. As it navigates, it observes more things. So in this case, it observes a suitcase, it adds it to its map, and then it looks inside the box using a camera on the end effector and finds that there's no ball in there, there's a cracker box. So then it updates its distribution, the particles change. This is we're visualizing but 3 or 4 particles here. So a very small subset of the, probably about 100 particles that were used. And the robot continues navigating, infers the next goal, finds another box, looks in the box, finds a ball, and then comes back with the ball. And we've done this over environments of various scales, indoor, outdoor, for navigation and mobile manipulation. Again, really there, the key is using language as a sensor to infer structure about the environment. That's both metric, topologic, and semantic. And so that's using language in the context of mapping. We've also done this in the context, more specifically in the context of manipulation, particularly manipulating objects with articulated degrees of freedom. So again, I want robots to come into our homes, so we'll operate in environments that are built by and for humans, and many of these environments have objects that are articulated, and manipulating these requires understanding their articulated degrees of freedom. So it could be a kitchen, whether it's an oven or a dishwasher, a refrigerator, like we saw in the video before. It could be a trunk, a faucet, etc. And just another video of people using a Jaco arm to manipulate something that is articulated, that push button. Again, here's another example, manipulating a refrigerator, a light switch, etc. So these are all sped up 2 times. So very involved tasks. Again, controlling this with the joystick control, switching between different modes of operation. And so you want to be able to automate this. And particularly we want to be able to allow robots to learn expressive models of these objects that allow them to manipulate them with minimal supervision. And so just like before, I showed this idea of giving a robot a guided tour of an environment where we narrate and it's able to learn a spatial semantic map, we do the same thing effectively with manipulation. So the robot opportunistically watches someone interact with things in their environment, articulated objects in particular, and we accompany these demonstrations with narration. So again, the key is to do this. Oh, yeah.
Oh,
Question?
sorry, I have a quick question.
Yeah, please.
Yeah, so I find this idea of using language as a sensor really interesting. And as you were describing this process of how the robot can listen to that guided tour and be able to come up with a better map and a better understanding of the task, I was also thinking if you've investigated having the robot plan to utter particular things so it can demonstrate to like the human who's giving the tour what it knows and then get more targeted feedback.
Yeah, that's a great question. So we've done some of that. So we've had some dialogue. So say in the context of the mapping, language is, there's a lot of uncertainty in language, and especially when you're referencing something that's outside the field of view. And so what the robot would do then is it would give you a visual rendering of its understanding of the environment. But it would also, so it's not quite the same as describing what it knows, but I will talk about that a little later. But the robot would ask clarification questions. So, you said that the elevator is across from the lab. Is it also down from the kitchen? Something like that. And ask clarification questions to resolve some ambiguity.
Do you, and to synthesize these kind of queries, are you using some kind of like info theoretic objective where you're like, wants to minimize entropy or something? Yeah,
yep, exactly. That's how we're doing it. So with the one approach I'm speaking to, it's very, it's a POM-DP. So it's, when we were doing it, that was the standard for dialogue management. So we were using a POM-DP with some tricks to improve computational efficiency. But yeah, so an information theoretic, and you can imagine more modern versions of that as well. Yeah.
Cool, thank you.
Thanks. So yeah, so we want to be able to do this, and again, with minimal supervision, really do this, as I said, opportunistically. So say, for example, this is an older picture of me where I was manipulating a refrigerator. And so I want the robot to be able to watch me do this, and I'll provide a description of what I'm doing, but knowing nothing about the environment a priori. So it says unstructured, really, of course, this is a structured environment, really, but it's cluttered. And the robot doesn't know which of the pixels that it's observing of the scene correspond to the object being manipulated, which are background. It doesn't know anything about me. It doesn't know anything about the degrees of freedom on the object. It just sees pixels moving in the scene. And in this case, RGBD pixels and no fiducials. And we want to be able to figure out how these objects are manipulating. And so again, I want to take this sequence, and what I want the robot to output is some low dimensional embedding or representation of this object that is, say, a kinematic model. So a learned kinematic model as well as visual appearance, and do this for other objects in the environment as I manipulate them. So in this case, a microwave that was in the environment, given the visual demonstrations and then the lingual demonstrations, the natural language descriptions. And then later, when the robot encounters those same objects, it can hypothesize how it might interact with them and actually go about interacting with them. And then, of course, these models are, the models that it's acquired are uncertain, when we're modeling that explicitly, and they're probably not going to be perfect. So as the robot starts interacting with this environment, we'd like it to be able to refine them based on the motion that it observes as it plays with the object, but also based on force feedback from these objects to correct any uncertainties or any ambiguity, any errors really in these environments. And as I mentioned before, this is challenging because the scene is cluttered. That kitchen was pretty cluttered. The objects are not known. We don't know how many parts there are. We don't know which part is connected to which. We don't know what's the object versus the human versus background. The visual and language observations are noisy. There are occlusions, et cetera, et cetera. And there's been a fair bit of work. And again, this is old by today's standards. So there was a lot of early work in modeling articulated objects by Dov Katz, who was a student of Oliver Brock's, doing this. And Jürgen Sturm had done some work using fiducials, so these checkerboard patterns. And then there's more recent work. So George Konadaris has a method. Scott Neekum has a neural method that assumes 2 degrees of freedom, and they're able to train this, and that's another avenue that we're looking at. But the model I'll talk about today is non-neural. And so this is the example, is we have an object, in this case, it's a filing cabinet that the person manipulates, and we have a description. So, a man pulls a drawer out, he then slides open the second drawer. And what we want to infer at the bottom is a model of that object. So what does that model mean? It means how many parts there are in the object, where the parts are in the scene, and then how these parts are connected. So that's that graph that's visualized here. So we use a graphical representation here as well. So each node represents a part, an edge indicates some kinematic relationship between parts, and then we have semantic attributes associated with these edges. So whether it's a rigid connection, a prismatic degree of freedom, or a rotational degree of freedom, and then the parameters of those degrees of freedom. So what's the axis of translation? How far does it open? How far is it open currently? What's the axis of rotation? How far is it open, et cetera. And then we can hypothesize in the lower right how an object might move, and then use that to then go about interacting with the environment. And so we model this probabilistically, as I mentioned before. We have a graph, and so what I'm visualizing here is a simple setting where we have 2 parts. So x1 and x2 denote different parts. Each green ellipse denotes a kinematic relationship between different parts. So it's a rigid connection, rotational, prismatic, or we can also do a local linear embedding or a Gaussian process. And then in most cases, we can actually enumerate all possible graphs, because most objects in man-made environments don't have more than maybe half a dozen parts. So we can enumerate all possible combinations. And we formulate this idea of estimating the articulation as selecting the graph that best describes the observations. So that maximizes the likelihood of the observations, and that observations meaning the RGBD image sequences as well as language. And then the one that fits a model to these objects, or to these observations rather. And again, that's how we formulate this as a problem of inference. So maximizing this likelihood, where again, we have a set of each Mij is an edge together with its semantic type. So rigid, prismatic, rotational, or a local linear embedding or a Gaussian process. and then the parameters of this model. And then we maximize this based on the observations. And I'll go through this quickly. I don't know if it's worth going through the individual approach. I mean, actually, I probably will skip the specifics. But the way that we do this is, I would say arguably, more traditional, in part because the data that we have for this is fairly limited. We have about 50 videos that we've collected for this. So the way we approach this is we take these image sequences and we need to figure out first how many parts are there and what are the different parts. So what we do is we extract a set of interest points. So we use good features to track. And then this gives us a set of trajectories of individual features. So I'm showing F1 through Fn are the trajectories of each one of those features. And then we cluster these to look for features that move in a consistent fashion using a form of spectral clustering. So that gives us, again, we don't know how many objects there are, and we group these to get a set of objects that move similarly. And then we take those trajectories and we formulate that as a SLAM problem. We build up a pose graph, and I'm happy to go into the details if you're curious. We build it up as a pose graph, and then from that pose graph, we optimize and we get an estimate of the pose of each one of these clusters over time. And then we use that together with language to fit a model of the kinematic model. There's the graph, or distribution over graphs really, and its type, and then the model, the specific parameters of those models. And again, I'll speed through this because it's not probably a little bit going too much into the weeds. Yeah, again, we use how we use language. Again, we use a variant of the DCG, again, publicly available. The implementation is publicly available to infer the set of objects, spatial relationships, and actions or affordances that are determined by language. Again, this is the factor graph representation. Again, I'll skip through it. Again, you've seen some April tags in here. Those are only for ground truthing. We actually mask those out to make sure we're not using any fiducials. So that's sort of our, we don't have a kinematic, we don't have a really true ground truth model of these objects. We don't have the CAD files. So we use the April tags to get an approximate ground truth. And so what we can do is we collect the data set where we have somebody interacting with various articulated objects, so laptops, microwaves, refrigerators, doors, etc. And then we use these observations to learn some, motion manifold. So that's the graph. It gets a distribution over the graph and the parameters of that graph. And then we encounter those objects again, and the algorithm is able to hallucinate or predict how this object moves and how the robot might go about interacting with them. Okay, so we evaluated this on a data set consisting of 56 demonstrations, each about 30 seconds, 10 household objects. I think it actually might have been more than 10. And because it says 25 single part, 31 multi-part objects. I think it's 10 different types. That's what it is. Fiducial markers just for ground truth. And we evaluate this again at the time, around 2017. What was the state of the art then? It's a method by Dov Katz. And we found that, again, without using any fiducials, no prior knowledge about the scene or the object, we're able to outperform both in terms of so lower is better and both in terms of the accuracy of our estimates of the model, as well as our ability to predict the motion of the object as it is manipulated. So that's, again, this idea of using language as a means of learning articulation models. So again, this idea of, this guided tour of manipulation, if you will. So, language plus, a form of learning from demonstration. And so that's using language as a sensor. So I think related to Andrea's question, another thing we've been looking at is not just, robots being able to understand natural language, but also using robots to be able to generate language, whether it's to, make the user aware of what they are knowledgeable of, or to convey information to the human that they themselves may not know. So you see many applications of this. So whether it's establishing trust, it's certainly important to have some understanding of what the robot is able to do and what it's not able to do. If you have a physical collaborative task, being able to generate language is important. Learning from tutors and establishing shared situational awareness, whether it's, say, a firefighting application. In this case, it's motivated again by the robotics CTA, where you have human soldiers teaming up. You'd like to be able to succinctly convey information to the human about what's relevant of the environment, what's pertinent. And so we looked at this using a surrogate task of navigation. So we were looking at this in the context of route level navigation. So sticking a human in an environment they've never been in before, and have them navigate that environment, going from point A to point B, given a natural language description. So the challenge there is to generate an instruction, ideally a succinct instruction that allows them to get to the destination as quickly as possible. So we looked at this, and so we formulate this as a form of what we refer to as selective generation. And so we've done some work more on the natural language understanding side of this, where the task is, we formulate the task as two sub-problems. One is take the robot's model of the environment. Maybe you can think about it as a database. So that's a map and that's a path. And we want to distill that down to a succinct amount of facts to convey. So there are many different ways, for example, that I could describe a path, many different objects and locations that I can reference. Sorry about that. What should I talk about? So that's the what to talk about part of this. And so you can imagine now, so it used to be that, Google Maps, and I think Apple Maps does it as well. When you get directions, they would reference distances or street names. I think for the last maybe couple of years now, they've also used landmarks, or I know Apple does, take a right at the second light. They might say in some areas, maybe they'll say, take a left at the Starbucks, or maybe there's Starbucks everywhere, and they won't say that. They'll say, take a right at the, at the gas station. So referencing landmarks. So that's a content selection problem. Do I talk about a landmark? Do I say go a kilometer down the road? Do I say take a right at Main Street, etc.? So that's content selection. And the next is surface realization. So given that I figured out of the many different things I can talk about and in what order, I've distilled it down to this small subset. Now, how do I convert that into natural language? And that's the surface realization problem. And so in terms of content selection, people may have preferences, in certain environments, it might be better to use distances, and others, it might be better to use landmarks. And so we collect demonstrations of people giving descriptions to one another, and we learn a policy. So we formulate this as an inverse reinforcement learning problem, where we learn a policy that takes as input a path, and again, there's a toy example here, but a path, a set of objects, really this database, if you will, and selects from that the most pertinent things to convey. So we do that, and that might be, then we take that and we feed that into a sequence to sequence model. Again, it's very much like what I was talking about earlier, these machine translation models for language understanding for robotics. We did some earlier work, 2016 on that. And this is effectively that model inverted, if you will. So instead of the input being English and the output being a path or a robot actions, it's the other way around effectively. So this will spit out, natural language. Again, this is a toy example. So, walk forward once, face the easel, move to the lamp. And so that's how we formulate this what they call selective generation, selecting what to talk about and how to talk about it. Okay, so we evaluated this. We had on this, if you may be familiar with what's referred to as the SAIL data set. So it's these 3D virtual environments, much like I showed in the video, where people had to navigate through. It has 3,000 demonstrations. So it's fairly small, not fairly, it's very small by today's standards. So these path instruction pairs, again, like people do at the time, they visualize the aligner. This is not really too interesting, maybe. And so what we did is we went on Amazon Mechanical Turk, and we had 42 people, and we flipped a coin. If it came up heads, they were given an instruction generated with our model, our algorithm. If it came up tails, we gave them the human example, again, from a held out test set. And we looked at things like how successfully did they reach the destination. And we actually found that they were slightly more successful, so 4% more successful when following our instructions compared to the human instructions. If people got their left and the right mixed up, so they made mistakes. And we asked qualitative questions on a Likert scale. How informative were the instructions that you were given? And they favored ours by almost 20%. How easy were the instructions to follow? Again, they favored ours by 20%. How confident were you that you reached the destination? Again, they favored ours by 8%. But then we asked them, was the instruction generated by a human or a robot? And they correctly guessed most of the time that, which ones were generated by a human and which ones were generated by a robot. And we were confused by that because the instructions really looked, quote unquote, natural to us. But we looked again, this is just speculation, but there are some subtle errors in our generation, like, not using a and an, not using and before a word that begins with a vowel. And so we think there are these subtle cues that they were able to pick up off of. And so again, this is just a toy example, and we've done this in other domains as well, but in the context of route navigation. So again, realizing robots that are able to generate language. And so with that, the second of two shameless plugs that I have. So we've been involved in Ducky Town. So that was the rubber ducks that Andrea mentioned earlier. So if you're not familiar with Ducky Town, it began with a class on autonomy and robotics at MIT in 2016. We all taught it, various people together, in 2017, and it involves taking these small scale cars with a Raspberry Pi or now an NVIDIA Jetson on it, and getting them to drive these rubber ducks in this town built for rubber ducks. It's cute. It's a long story why it's rubber ducks. But it was a class initially, and now we've extended this to use that as a platform for benchmarking progress in autonomous driving, and maybe more generally, learning-based methods for embodied tasks, navigation in particular. And so for the past, I think we've had, 5 or 6 of them started in NeurIPS. And so this coming NeurIPS, we're going to have IDO 6. So this challenge, the link at the bottom, it provides all the information in terms of joining. And we have a high fidelity simulator, a bedroom simulator coming on board. We have these remote, what we call auto labs, or we stole the term robotarium, where you can train, test, and evaluate your code on a real Ducky bot running somewhere in the world. There are 2. So there's one at TGIC here, and then there's one at ETH Zurich, with cameras all around the town doing sub-centimeter, really millimeter level localization. And you get a score back, you get all the data you can use for training or evaluation. And we'll use that for the test, unfortunately, because NeurIPS is going to be virtual this year. And it's a really fun platform with a lot of applications beyond benchmarking and beyond, graduate level or college level education, a lot of outreach opportunities. And because the platform really is meant to be accessible in many senses of the word. So, and there's one thing I didn't talk about really, because it was just really last minute. So recently we got back from this cruise off of Los Angeles, where one thing we've been looking at is taking some of the tools that I talked about, the capabilities that I talked about now, and using them to allow scientists, so not non-roboticists, to control underwater robots performing intervention operations. So we had an underwater robot called Nui, 1,000 meters deep off of Los Angeles. This robot has an arm on it, and we're able to do remote sensing and sampling using with a scientist from Chicago and scientists from the Woods Oceanographic Institution, literally talking to this robot that was thousands of kilometers away, and then a kilometer deep below the sea surface, providing natural language commands to perform sampling operations. And so that was just a couple weeks ago. So I was hoping to get a video together, but didn't. So anyway, with that, I want to thank, there are many people that were involved in this work. This is just a small subset of them. And the papers that I referred to, I think you saw the notes that were there. They're all on our website, so ripple.ttic.edu. If you have any questions that aren't answered today, feel free to email me. And with that, thanks again for the chance to visit.